Do you want to protect yourself and your kids from some BS you were told? Are you a quitter? Can you focus? If you're still here, then this might be for you. There is a catch, however. It's not easy. There is going to be details. No BS. Did you know, in mathematics there are no proper definitions for numbers, infinity and continuity? You were told, here's 1, 2, 3, 4, 5, ... You can always add 1. Infinity is what is not finite, and what finite is, you already know. And last but not least, here's a continuous number line, because you can put infinitely many numbers between two neighboring numbers. Look at the official definitions now for a moment, pause the video and smile. What is true of what they told you? They gave you a few numbers, that was true. I bet you, though, you never saw a number bigger than a few pages of digits, probably for a symbol like pi. The rest they told you was all BS. You cannot always add 1. You cannot define infinity properly. You cannot define continuity using numbers, and the number line is not continuous. If you now say, who cares, then stop watching. Still here? Excellent. There are consequences to the production of BS. Mathematics with numbers is always discrete, and continuity is approximate. To a physicist, his measurements were always approximations, but his models, thanks to mathematics, were exact. A mathematician thinks mathematics is precise, and the definitions, the axioms and theorems are true. But some of them are not. So the mathematician is not as trustworthy as he himself or the physicist thought. This is okay for a while, but when you get money for infinities, multiverses, wormholes or time travel, something has probably gone wrong. Now, let's focus. In mathematics, we talk about things like points, lines and planes. If you were to put them on paper, according to current definitions, you would see nothing. When in real life we draw points, lines and shapes, they all have volume, even on a computer screen. We prove theorems using definitions, axioms and already existing theorems in mathematics. And axioms are things we think are true, but we know we cannot prove. If a statement is not proven yet, it's called a conjecture. Definitions and axioms are our beliefs in mathematics. They better not be corrupted. Spoiler alert, some are. The cause of it all? Something that went unnoticed happens when we make distinctions. Making distinctions happened. Here's a quick summary. 1. Mathematics has not formalized the intuitive understanding of continuity. 2. Infinities and irrational numbers are like gnomes and fairies. They do not exist. 3. The scientific method is not almighty. It can only probe our perspective, not the underlying machinery. Nature protests when we look closely enough. The distinction between 0 and 1 has consequences. Our intuitive understanding of continuity cannot be precisely described, because the concept of infinity cannot be properly defined. When drawing a line, my intuition tells me that my pencil is continuously moving. A black line appears. The intuitive line and the number line should both be continuous if you want to completely compare them. The number line, built from points, remains a kind of Swiss cheese until you are able to introduce the concept of infinity. The idea is that with an infinite number of points or numbers, you can fill the number line completely, making it a direct, exact representation of the intuitive line. One should always be able to place a new number between two neighboring numbers. But concepts have to be defined precisely in mathematics. The concept of infinity, as it is now, is based on what we call finite. Something is infinite if it's not finite. In doing so, finite is still to be defined. We conveniently assume that we can always add 1 to a number, but we can't. The numbers become too big. Very soon, they no longer fit in the visible universe. At some point, the numbers can no longer be expressed, identified, or distinguished from other numbers, and they can no longer be used for calculating. Even adding 1 becomes impossible. It cannot be done in space or time. Numbers disappear into big number land. We never get to see them. Big numbers are no longer properly defined numbers. It should be big symbol instead of big number. The suggestion of a few numbers we fabricate in the big symbol realm is really only done by symbol manipulation. And this happens long before you reach infinity. Infinity disappears. The concept of infinitesimal also disappears. This concept also doesn't work, because there is no time and space to put enormous amounts of digits behind the decimal point. Other well-known concepts disappear as a result, such as pi and e and the square root of 2. The concept of number has to be defined properly using symbols, and it's not proper to have a plus sign or minus sign or another operator sign in the middle of a number symbol string. ... isn't proper either. We fooled ourselves into thinking we were being exact. We were not. Fortunately, we can still calculate approximately with the irrational symbols, and we've never done differently. Take, for example, the ratio of the diameter and circumference of a circle. This ratio cannot be precisely described with a number. Therefore, in addition to the really big rational numbers, we lose all irrational numbers, countable infinity, and all other types of infinity. These belong to the world of fairy tales. We have never seen or used them, nor will we. Sometimes you hear that you can in principle always add 1. But what does in principle mean? I've never received a satisfying answer to that question. The question is mostly ignored. The answer, if given, is ultimately that we must agree to disagree. I find that unsatisfactory. It's nonsense. Give me a proper argument and proper definitions. So, in summary, in exact mathematics, we lose the continuum and infinities. But in approximate mathematics, it all still works. The numbers we encounter and produce are by definition small enough to handle. Back to the distinction between 0 and 1. As soon as numbers are used, we are talking discrete mathematics, even if some mathematicians still think otherwise. The geometry of the ancient Greeks is continuous when it comes to, for example, lines, planes and circles. On the line and in the plane there is continuity. but in the dimensions perpendicular to the line or the plane there is discreteness, as with a point in all dimensions. An intuitive line, plane and volume are not composed of points. An intersection point of two lines distinguishes that specific place from the rest of the two lines. It's a special point, a touching point, that connects and touches in-betweens, where in-betweens are continuous pieces of line. The special touching point connects four in-betweens. So, we use a touching point as glue to connect in-betweens. This is only necessary for lines. In more dimensions, there's always only one in-between, sampled by touching points, using numbers. To be clear, touching points only exist on paper, like gnomes. What would it look like on paper or screen? If you were only allowed to draw points using current mathematical definitions, you don't see a point, you don't see a line, you don't see a plane or a volume. You see nothing. Even if you add the in-between to mathematics, you still can't create or see points, lines or planes on a screen, because they lack at least one dimension. You can create and see volumes, just like we do on a real screen. In physics, making distinctions also has consequences. Conjecture is that there is no distinction or separation in reality, but we can perceive distinctions and separation. The measurement evidence gives a first indication of the absence of distinction. Unfortunately, we haven't so far interpreted it that way. New research is necessary. Here is a model to show the distinctions we make. 1. Our human perspective is the perspective that makes the distinction between measuring device and the environment. In the picture, the letter A indicates this separation. We seem to see a clear boundary between our skin and the air. We see the apparatus. But if we look closer, that boundary becomes blurry and disappears. We are not separate from the environment. 2. In modeling on paper, the observed system of particles is central. Our measuring devices, separated by A, return bleeps and stripes and more. In the picture, the letter B indicates the paper separations between measurement device and the system of particles. The letter C indicates the paper separations between the measuring setup and the rest. Everything very small on paper, such as an elementary particle, behaves strangely in the reality of the human perspective. Classical mechanics gives way to quantum mechanics on paper. In the human perspective, predictable measurement results are replaced by measurement results with a statistical character. There is a chance of that something will happen, but no longer a certainty. Sometimes you get one outcome and sometimes another, but always according to a fixed statistical pattern on paper. To represent the statistical behavior of a system of modeled particles on paper, the minimum separation that we can think of is that between two objects, called a tensor field and space-time. Tensors are composed of groups of numbers that meet certain calculation criteria. 3. The scientific method connects paper order and order in the human perspective on reality. Separation B and C are compared to separation A. The analogy between what is on paper and what comes from measuring instruments must be correct. The scientific method provides clarity through the process of measuring and distinguishing. The scientific method can only disprove a theory. It cannot prove a theory. But maybe there is no distinction in nature. Nature may be one continuous material, able to deforming into emerging measuring devices like people. The scientific method cannot directly discover that material. Whatever device you build is made of that material. Because separations A, B and C do not exist, measuring and modeling will only provide indirect evidence for the conjectured unity, and this happens in the form of quantum mechanics. 4. Another problem in contemporary science is that we don't know what nature is made of. So far, we have managed in physics with the symmetries of that substance. This has allowed us to develop quantum field theory. However, discrete fields of numerical constructions do not constitute real material. I suspect that we need to take a step further and investigate if nature can be built from a continuous substance. I conjecture that in nature there is no distinction at all, but local distinctions can evolve by the different properties of that one material. 5. Time is perhaps the trickiest concept in physics. We feel in our guts that things change, and for that we have conceived the concept of time. Change is a physical property, the most undeniable physical property, it would seem. Time is a physics concept, a human concept, a paper concept, to describe real change on paper. To compare time to change, we build space-time geometries, also known as clocks. They change quite predictably, giving continuous and discrete data. We have discretized paper time because we use numbers. If change is continuous, numbers are not enough to grasp the concept of change. A duration of time must be an in-between. Current mathematics does not yet include that concept, and I say, add the in-between to mathematics. It is our confession of inability. In current physics, it is sometimes claimed that change is discrete, but that is based on discrete mathematics and without underlying physical machinery. Again, continuous time as a physics concept to describe continuous change cannot emerge from discrete mathematics. We need the in-between. We need this confession of inability. In summary, making distinctions has consequences for both mathematics and physics. In a nutshell, in mathematics we use the continuum, infinities and big numbers. In physics, we need a new machinery and material description. The scientific method is not sufficient to probe this material directly. The machinery for change is probably the most elusive. For now, we have only been describing our perspective on reality, not reality itself. Doing what we have always been doing in developing our perspective must obviously go on. There is, however, the opportunity for a new field of science. Read about it in the book New Perspective.